Welcome to Statistical Inference. Have you ever wondered how we can predict the outcome of a national election by asking just a few thousand people? Or how we know a vaccine works for billions by testing only a small group? This magical leap from a small sample to a massive population is the heart of statistics. Today, we are going to build your understanding of the concepts of estimation from the ground up. Let us dive in. To understand estimation, imagine you are cooking a massive pot of soup for a party. You cannot drink the whole pot to check the salt. Instead, you taste one spoonful. In statistics, that entire pot is our population, and the spoonful is our sample. The true saltiness of the whole pot is a hidden fact we call a parameter, usually represented by the Greek letter theta. Because checking every item is impossible, we use the sample saltiness, called a statistic, to make a highly accurate guess about the whole pot. Now that we know what a sample is, how do we actually make that guess? We use a mathematical rule called an estimator. Think of this as the recipe for our guess. Here, T represents the estimator. The function h tells us what math to do, like adding or dividing. The variables x1 through xn are the actual data points we collected, and n is our total sample size. By plugging our data into this function, we build a mathematical bridge from the data we have to the hidden truth we want to uncover. Once we apply our mathematical rule to the data, we get a specific number. This brings us to our next formula. The symbol theta with a little hat on it is pronounced theta hat. In statistics, putting a hat on a Greek letter universally means an estimate of that parameter. While theta is the true hidden reality of the population, theta hat is our best mathematical guess based on our evidence. If we took a different sample, our estimate would change, but the true parameter always remains a fixed number in the background. Let us visualize this entire process we just discussed. On the left, you see the massive population with its unknown parameter, theta. We cannot measure all of it, so we follow the top arrow to draw a random sample. This gives us our manageable data points, x1 through xn. We then feed this data into our estimator, the grey box representing our mathematical rule. Finally, out pops our estimate, theta hat. This diagram perfectly summarizes the core engine of statistical inference. With the general process clear, let us look at a specific scenario. Imagine a farmer wants to know the true average weight of all 10,000 apples in his orchard. This true average is our population parameter, often written as mu. Obviously, he cannot weigh all 10,000 apples, so he picks just 5 apples at random. Their weights are 150, 155, 148, 160, and 152 grams. How does he use this small group to guess the average of the entire orchard? To solve the farmer's problem, we need a specific estimator. We will use the sample mean. Here's the formula. The symbol x bar represents the sample mean. To calculate it, we add up the individual weights of our 5 apples, represented by x1 through x5. Then, we divide that total by n, which is the number of apples in our sample. This simple averaging process gives every apple an equal voice. As the sample size n increases, this estimator generally becomes much more accurate. Now that we have our formula, let us put it to work. We start by substituting the actual measured weights of the 5 apples into the top of our fraction. The abstract variables are replaced by 150, 155, 148, 160, and 152. We also replace the sample size n at the bottom with 5 because we picked exactly 5 apples. We have transformed our abstract rule into a simple arithmetic problem, and we are ready to add them up. Continuing with our calculation, we add the 5 numbers together. The sum is exactly 765, This means our 5 sampled apples weigh a total of 765 grams. The denominator remains 5. Finally, dividing 765 by 5 gives us 153. Therefore, our estimate for the true average weight of all 10,000 apples is 153 grams. By weighing just 5 apples, we made a highly logical, data-driven guess for the entire orchard. Let us explore another common type of estimation. Suppose a factory produces 50,000 light bulbs a day. The manager wants to know the true proportion of defective bulbs, which is our parameter P. She cannot test all 50,000, so she tests a random sample of 200 bulbs and finds that exactly 8 of them are defective. How do we estimate the true proportion of defective bulbs for the whole factory based on this small inspection? To figure out the factory's defect rate, we use the sample proportion estimator. In this formula, P hat represents our estimate of the true population proportion. The variable X stands for the count of what we are looking for. In this case, the number of defective bulbs in our sample. The variable N is our total sample size. This formula simply calculates a ratio. If the number of defective bulbs X increases while our sample size stays the same, our estimate P hat will also increase. Let us apply this proportion formula to our factory data. We found exactly 8 defective bulbs during our inspection, so we replaced the variable X with 8. We tested a total of 200 bulbs, so the sample size N is replaced by 200. This sets up a simple division problem, representing the fraction of bad bulbs in our small group. We assume this small group rate will be a good guess for the entire factory's production. Finishing our calculation, dividing 8 by 200 gives us a final decimal value of 0.04. This means we estimate that 4% of all the 50,000 bulbs produced in the factory that day are defective. The manager can now use this estimate to decide if the machines need maintenance. We successfully guessed a crucial fact about 50,000 items by only looking at 200 of them. Before we wrap up, let us reflect on why this matters. Estimation is absolutely crucial because we can almost never measure an entire population in real life. It acts as the logical bridge between the small amount of data we can actually see and the massive hidden truths we need to know. Without the concepts of estimation, society would be paralyzed. We would be unable to make scientific or business decisions unless we had perfect 100% complete information, which is practically impossible. Let us review our key takeaways. We learned that a parameter is a hidden truth about a massive population. To find it, we use an estimator, which is a specific mathematical rule applied to a small, manageable sample. This calculation produces an estimate, a final numerical guess. By mastering this fundamental core tool of statistical inference, we can save immense amounts of time and money while still uncovering highly accurate insights about the world around us. Great job completing this topic.